All right. Well, welcome everybody, and thank you for joining. My name's Ashley, and I work with the Confidential Computing Consortium. We're excited to pick our webinar series back up after a short summer break, and today we welcome Dave Thaler speaking on attestation. Dave, I'll let you take it away.
Great, thanks, Ashley. So welcome, everybody. I'm actually here sort of wearing almost two hats, if you will. So I chair the Technical Advisory Council in the Confidential Computing Consortium, which hosts this webinar series. The consortium does. I chair the group that does the technical parts within the consortium, but I'm also an editor in the IETF work, which is the standards body that does a bunch of work that's done, TCP/IP and HTTP and lots of other things on remote attestation. And so I'm kind of representing both groups here. We actually have a number of participants in common between the CCC Technical Advisory Council and the IETF Remote Attestation Group. And so this is kind of a collaborative effort across a bunch of people in the industry, and I'm just one of the people that gets to talk about it today. So again, welcome. Thank you for coming. So let me first talk about, what is the IETF if you're new. The IETF, and specifically the RATS working group, right? RATS is kind of this backronym, right, where it's kind of somewhat for, as you can see, it stands for Remote Attestation Procedures. So you can call it Remote Attestation Working Group. You can call it RATS Working Group. If you heard the term RATS, that's what it means. Within the Internet Engineering Task Force, right, this is the standards body that does lots of the network layer all the way up to applications layer things that interact with a bunch of other organizations, right? It doesn't do typically layer 2 formats like Bluetooth and Wi-Fi and so on. Those are other organizations, but the IETF does a lot of the networking standards. Okay. Within the overall IETF, there's a bunch of different working groups that all have a charter to do a specific task or do a specific subset of the overall functionality of the internet. So the Remote Attestation Procedures Working Group has a charter. Okay, there's actually a little link to it if you get the slides afterwards, but you can get to the link through any other URLs on the slide. This one is chartered to do architecture and data formats around this problem of remote attestation. I'll define on the next slide. And so you can see there's a URL there that says, here's where the documents are stored for this working group. Right, the IETF working group meetings is all public. It happens on mailing lists and in meetings which are open to all attendees and has virtual attendees and so on. So it's had participation from a wide set of the industry, including representatives from other standards bodies, such as Trusted Computing Group and FIDO and so on and so forth. So that's why it's really easy to have coordination across the industry within an organization like RATS, because it's open and invites participants from all these other organizations, Global Platform and Trusted Computing Group and so on. So everybody kind of comes together in this open forum to discuss common problems that span across many of the other segments of the industry. And so that's actually kind of our key, one of the key points of context for the CCC, right? When we work with other organizations, whether it's, TCG or IETF or whatever, the IETF being a fairly open organization, that's where we tend to have a lot of overlap between participants, right? Because the CCC meetings are themselves open and public, and the IETF meetings are open and public. And so it's really easy to have a common set of participants that go back and forth and participate in both, okay? And that's where a lot of this effort came from here. Now, of course, the Remote Attestation Procedures Working Group has a wider scope than just confidential computing that we within the CCC are interested in. And so some of this is going to be talking about an architecture that can be used for both confidential computing and other things. So for example, if you have a communication, one side might be using confidential computing, while the other side is not, and you want mutual attestation. And again, I'll define that on the next slide. And as a result, you have things like a main architecture document from the IETF, which is almost done. It's what's in last call stage, if you understand what that is. It means it's about to become an RFC being the IETF term for a published standard. And the Confidential Computing Consortium did a technical white paper that the TAC did a while ago, which we had a webinar on earlier in this series, which you can find in the webinar archives. Both of those two documents cross-reference each other, again, because a lot of the participants were in common, and any feedback received in one organization has been incorporated back into the other one so that they are intentionally kept consistent. This is a good thing. Okay, so let's make sure we're on the same page. What do we mean by attestation? Well, if you're at this webinar, you probably already know, but if you're just watching this webinar after the fact, let me give you a quick introduction in one slide as to what it means. And this language comes out of the RATS architecture document itself. And so there's not a formal definition. It's kind of defined in layman's speak by example, okay? So the closest thing to a definition of attestation is to verify that some system or piece of device or piece of software is in a good state for some value of good, right? The concept of attestation doesn't define what good means. It's the procedure by which you decide whether some other entity, whether some other peer is actually in a good state or not. It's that process and the protocols and the formats and things, okay? The policies is what is your definition of good. So here's two examples that are called out. One, you might have a bank's backend system that wants to refuse to transact with some other system, whether it's a payment terminal or a phone or whatever else, that is not known to be in a good state, right? You don't want to interact with, say, malware or something, right? Somebody that's out of date that doesn't have the latest security patches, for example, right? Another example, a healthcare system that cares about privacy of healthcare data might refuse to transmit electronic healthcare records to something that's not known to be in a good state, okay? So in other words, it's not if it's known to be in a bad state, is if you can't prove, or at least you can't assert with high degree of confidence a convincing argument that says that you are indeed in a good state, right? Because if the receiver says, well, how do I know you're not lying, right? Because if there's malware there, malware can lie. How do I know that what you say is true? And that's what attestation is all about. So in remote attestation procedures, one peer, which we refer to as the attester, is what needs to present, to produce to their side believable information about itself, okay? That information we call evidence, okay? There's more specific terms used in different industries and different protocols. The generic term that we use when you're supplying information about yourself that somebody else can then evaluate or appraise is the term that we use. To decide whether they believe it, we use the term evidence. And so the relying party is the receiver of that information and needs to decide. So for example, in the bank example, the relying party is the backend bank system that gets to decide whether it wants to transact with some other system that wants to connect to it. Or similarly, in the healthcare example, the relying party is the system that wants to decide whether it's going to transmit electronic healthcare records to the other side based on evidence presented from the other side. So that's kind of what attestation is. So now we're going to dive into what's the actual architecture, because the concept of attestation is not new, right? It's all over the place in many systems today, okay? The problem today is that all the systems tend to be proprietary systems or special use case things for a particular case, as opposed to something that is broad and standard. So the IETF was taking all of these previous prior art or prior examples of deployed systems of attestation and says, how can we agree on having one common framework or one common protocol that could be used? For example, what if I have heterogeneous attesters? Okay, what if I have, in confidential computing, what if I have one that's running, say, an ARM system, and one that's running an Intel system, and one that's running an AMD system, and one that's running a RISC-V system, and they all want to mutually attest to each other? How do we do that? Okay, that's the type of problem that the RATS working group set out to solve here, is to have a common architecture, but not, I go back a second, not the actual protocols or codes. This is kind of the step one. There might be standardized protocols in the future. There might not be. And so that's kind of left for a future work. But the point is right now to have common formats that can be used within existing protocols. Because it really turns out that it's about the formats. It is what's the data model, if you will, for doing attestation. That's the key task that tends to unblock things. So, all right. So the architecture that RATS has put together had a number of example use cases, right? And it's not limited to these. These are pure examples, okay? But it helped to ground the architecture that says, we have better confidence that the architecture is general and standardizable and reusable across things if we can have some confidence that it's directly applicable and as many use cases that people care about now as possible. And so here's a number of specific use cases that the IETF used as example use cases. Again, not specific to confidential computing, but pretty much everything on here you can do in a confidential computing case. Okay. I see a question coming in, which I will get to on a later slide about what good state means. So hold that thought and I'll get to it in a little bit. So a number of these use cases, and I'm not going to cover all these right now, but I'm going to pick an example or 2 or 3 on here to show how all of these are relevant to confidential computing, even if the original use case is broader than just confidential computing for some of these. So let's just take, number 1, network endpoint assessment. So the use case here is I only want to let a particular device onto my network, okay? Maybe it's a private corporate network or something, right? I only want to let it onto my network if that is in a good state, not bringing in malware that's going to be attacking the devices on my network. A specific subcase of that is where the thing you're letting on is in fact another router, right? And so the routers are exchanging routes to keep the network up and running. And how do I know that all those routers are exchanging the correct information? And so this first use case, there's work around how do I do this when the attester is a router and the relying party is, for example, another router and they want to peer. Example number 2 is 2 and 3 actually come directly for 2, 3, and 5 come directly from the confidential computing world. Number 2 is one of the most popular questions or popular use cases, both for IoT devices, devices that run on premise somewhere and have some, direct control loop in them. Say, you have a camera that's in there and the camera is trying to recognize whether the product on the assembly line is good or goes into the bad bin, that kind of thing. And so these things often run machine learning models, right? The inferencing happens somewhere else, but the actual running of the model, the decisions that it outputs can happen live, right? And so the companies that manufacture these things want to protect their IP in these models. They want to run these models in devices that are under somebody else's physical possession, right? Their customer, right? And they want to protect it from being, say, bought and reverse engineered by, say, a competitor, right? And so whether you think of this as code or whether you think of this as data depends on how familiar you are and how you do the machine learning model, right? Those of you familiar with machine learning models might think of this as data. A salesperson might think of this as code. And that's why it's separated from example use case number 3, which is specifically about, I want to protect data, like the healthcare data we talked about before, okay? But I only want to present the data, or number 2, if it's code, the code to an entity that is actually in a good state that I'll come back to. Ben asks, does use case commonly used for zero trust deployment? Yes. Okay. So yes, if it's not clear, feel free to ask questions. Some of them I'll defer to the end, but please ask the questions live as we're coming along so we don't forget them. Again, some of them I'll take, some of them I'll leave until the end. So maybe the last one that I'll take, and I'll come back to this one later, is number 5, the trusted execution environment provisioning. Right. So I have a workload that I want to be run inside of a confidential computing environment. Okay, I want to provision that into the environment in a way that nobody else can tamper with that. So of course, I only want to provision it into there because it might include secrets inside my workload, right? It might include some data, some configuration stuff that I don't want to share with anybody else, including whoever is hosting that workload. Okay, so how do I provision that in a way that's confidential? Well, of course, the place that I'm going to provision it into becomes the attester, and the entity doing the provisioning becomes the relying party. Okay, so I only want to put the workload in there if I know that it's in a good state. All right, for any of the other ones, feel free to look at the architecture document. Let's go on. Hopefully that's a representative sample. Okay, so in our use cases, we've often talked about this notion of an attester and a relying party. Now, often these things will come from a pre-existing use case, right? You've already got an attester and you've already got a relying party, but you weren't using attestation. So if you think about a banking flow, right? I've been using the banking flow, or I've been using this healthcare application, and now I'm kind of the owner or the developer or the security analyst or whatever, and I want to add attestation in there because suddenly I've decided that, oh, malware is a problem, for example, or secrets leaking out is a problem, and I want to turn something into a tested case so that I can add confidential computing into a case that might not have been using it before. And so the existing communication is what's shown here in the line here that I want to add attestation to. Okay. So for example, often the relying party might be a server like an HTTP server, and the attester might be a client like an HTTP client, but it could also be the other way around. Okay. So we're just going to use that as an example. All right. So in order to do attestation, we need the involvement of typically a third device or third service here that's conceptual. That's called the verifier. Now, if you remember before, we defined the term evidence as being information about the attester that needs to be evaluated or appraised to decide whether that attester is in a good state or not. Okay. The determination of whether that evidence is considered trustworthy and the state described in the evidence is in fact the correct state is up to the entity called the verifier, not the relying party. Okay. I'll give an example later on where some of these roles can be defined, but in general, these are three separate and distinct roles, even if they're running on the same physical device. The verifier then generates some output that's attestation results, right? It's the results of that appraisal. It's an assertion that the attester is in a good state according to the verifier, or that it's in a bad state, or maybe it's a lot more refined than that. So attestation results could be as simple as a Boolean. Yes, it's good. No, it's bad. Or it could be a whole lot of more specific data that the relying party can use to apply its own policies. Okay. So for example, you might have a variation of attestation results that the relying party uses to grant different permissions, right? Read permissions versus write permissions, or access to data set A versus data set B, for example. Okay. So in that case, there's actually two types of appraisal, right? There's appraisal of evidence by the verifier, and there's appraisal of attestation results by the relying party. And that's what then brings in these other two things, which are not really about the runtime roles, if you will, but at some point you have to have somebody that provisions the verifier with that appraisal policy. We call that entity the verifier owner, right? So somebody's responsible for configuring the verifier, whether it's at runtime, statically, whatever it is, with appraisal policy for evidence. How do you decide, given evidence and perhaps other data, whether that evidence says that that attester is in a good state or not? Or to what extent? What does good mean? Okay, what does good mean is up to that appraisal policy for evidence, and the verifier owner is the author of what does it mean to be in a good state. Okay, so every verifier owner, and even the same verifier owner for different categories, can have different definitions of good, all expressed in appraisal policy for evidence. Similarly, whoever owns or manages, by owner, it could be the admin. The owner is used loosely, right? The relying party owner is responsible for configuring the relying party with whatever the appraisal policy is for attestation results, right? So how does the relying party take those attestation results and map it into something that's like an ACL, an access control list? How do I decide whether to make a decision that's good or bad for a particular operation, right? That's what the appraisal policy for attestation results is. Okay. All right, I'm going to keep going here. All right. So I mentioned the appraisal policy for evidence might use other information besides just the evidence. Okay. In practice, this is typically necessary. Again, these are all the possible roles. In many cases, some of these roles are collapsed and the same device or organization or person plays more than one of these roles. But in general, these can all be completely separate. Okay, so let me talk about the two ones that were just added. Okay, top left, endorser and endorsements. Typical example here is that an endorser might be a device manufacturer, especially a manufacturer of a security chip, right? So if we were talking about an Intel chip, this would be the something that can vouch for Intel inside, the fact that it runs SGX or whatever. Okay, same thing if it's an AMD chip or whatever else, and you have the specific manufacturer. Or if it's an ARM chip, it might be somebody like an NXP or whatever. This is really an authentic chip. You can trust the hardware because it has my signature on it as the manufacturer. This is an authentic one and not somebody else's knockoff that just claims to be that in software, right? So this allows you to construct a trust chain that goes back from the information coming out of the hardware on the device back to the manufacturer of that device. Okay, again, typically the endorser is a manufacturer, but it could be other entities in the chain. It could be, an OEM that assembles things together. It could be a reseller, but it has to be somebody that the verifier will trust. Okay, the verifier can choose who they'll trust, right? Whether they choose to trust a manufacturer, whether they choose to trust a security analyst or whatever, the verifier gets to choose who they trust. Okay, and so in this case, the endorser is who the verifier chooses to trust, whether it's a manufacturer or somebody else. Okay. So endorsements are typically statements about a device that the device can't make itself. And they're typically signatures over something that is unique to that hardware in the attester. So therefore, the attester's software or malware can't modify it because it's unique to the hardware. Okay, it doesn't have to be that, but most endorsements are in that category. Then the next little piece here is in the appraisal policy for evidence, right? I might have a policy that says, okay, I know that it's running a chip from my favorite manufacturer A, or maybe I support multiple of them and I have different appraisal policies for manufacturer A versus B, okay? Because this is a standard, right? Or the architecture is. And so based on the evidence and the endorsements, I can get a pretty good idea of what the current state is, okay? Now, if I can tell what the current state is in a trustworthy fashion, that still doesn't tell me whether it's good, because I got to know what the desired state is, right? The desired state is the one that has all the patches applied and so on, right? So how do I know what's the desired state? Okay, well, that's where the role of the reference value provider comes in. What is the desired state? Okay, and often the appraisal policy might be a check for saying the current state fits within the bounds of the desired state. Okay, now that's not always equality, right? Appraisal policy can sometimes be a lot more complicated than that. It could be it's a member of the following, any of the following values, or where aspect A is greater than aspect B in terms of those two values in the evidence, right? So it can be fairly complicated pieces of things in the appraisal policy for evidence. Particularly they have inputs that are the evidence, any endorsements that the device couldn't have provided itself, and any reference values. And again, any of those entities could be combined in many cases, such as maybe the reference value provider happens to also be the manufacturer. But in general, it doesn't have to be. And again, the verifier is what gets to choose who they trust. All right, and then the same thing will kind of be true, not shown here, inside the relying party. The relying party also has to make a decision about current state versus desired state, and you could have reference value provider values being used by the relying party's appraisal check as well. Okay, so those are all the different entities in terms of the roles that are used in the architecture. How you assemble those roles and how you map them to real use cases can vary by processor vendor or use case or relying party or whatever. These are the building blocks that you can use to construct a specific attestation solution. All right, I see there's a couple questions, but I'm gonna keep going and I'll take them at the end. So, but yeah, thanks for asking the questions in context. All right. So let me dive into a little bit inside the attester, right? We had that box there, that's the attester. I'm now going to blow up that box and kind of zoom in. Okay, so the dashed line here is that box. Inside the attester, there are a couple of different types of environments. This is showing that verifier, that's that piece of the picture, just to show you what talks to what here. When we look inside there, there's two types of environment inside the attester. Okay, and this is showing a very simple case with just one of each. Okay, there's an attesting environment and a target environment, right? And so what happens is you never trust something to generate information about itself, right? Because it can lie, right? And so you always ask somebody else to generate the information and signatures over information about you. Or in this case, the attesting environment A is what collects information about the target environment, B here, signs it and puts them in the evidence, right? That way, B can't lie because A gets ultimate control of whether it will sign that or not. If A doesn't have a reason to believe information about B, it won't sign it and put it into the evidence. So for example, that attesting environment A might be a piece of hardware. In fact, in hardware-based TEEs, it must be a piece of hardware that's at the bottom here, okay? And so you can think of cases where the attesting environment might include a TPM chip. It might be something that's directly embedded in the main processor, such as in, let's say, an SGX case. But the point is, the bottom here, in order to be fully trustworthy, that's a piece of hardware that can then be vouched for by a particular manufacturer, say through endorsements. Okay, the target environment here is just passive. So often what happens is the attesting environment will measure, let's say, a binary, and if it's good, then it will decide to say boot and start that environment B. Okay. That would be typical in like a secure boot case. Okay? And so the evidence is generated by the signature of the bottom, and then that's what's used by the verifier. Here it shows an arrow coming out of the attesting environment A, but once it's been signed, that arrow could be indirect, right? That arrow could be, it provides it up to target environment B, and it's just a signed blob that can't be tampered with. And target environment B can then supply it to anybody that wants, whether that's a verifier or somebody else. So it doesn't mean that the protocol is done by the attesting environment A. It just means the signed data, because again, what we're standardizing in RATS is not the protocol, it's the data format, right? So the data format, the signed blob, the token is signed by, in this example, A, and who it's transmitted by could be B or anybody else, okay? But it can't tamper with it because it's already been signed, okay? So that's a testing environment and target environment. All right, and I mentioned that endorsements you can have typically for A, but you can also have endorsements for B, right? If somebody else wants to say, okay, well, B is a piece of software. I'm the manufacturer or the vendor that created that software, and I'm going to provide some other information about, say, the supply chain of B. Not about the current state, but how it got to there, and maybe what process we used, or just the fact that it was created by, in my case, Microsoft, or, created by open source project, whatever, under the following, license could be. Okay, so the point is endorsements are a pretty broad thing that can be anybody else that the verifier might trust that has information to provide about anything that's inside the attester might be relevant. All right, and then similarly is true for reference values, right? What's the correct state of B, right? Does it have all the patches? Well, probably the entity providing information about A might not know the correct values for B, right? If those are two completely different pieces of software or hardware or whatever. And so you might have different reference value providers as well in general, okay? You might also have one reference provider that collects information from other ones. But again, this is showing the general case and the definition of roles. Now, what I showed before was a very simple case where there was one testing environment and one target environment. Most real world cases don't do that. Most of them have multiple layers of things. So this notion of layered attestation or layered evidence shows up in lots of different places, TCG, global platform, and so on, IETF. And what happens here is once you have a target environment that's been signed evidence by a testing environment, that target environment can then become an attesting environment for another layer up, okay? So for example, A might be hardware, B might be firmware or a bootloader, C could be an operating system. So in general, there can be any number of levels here. If you go all the way up from, hardware all the way up to say, an application layer through, bootloaders and firmware and microcode. So really how many layers there are really depends on how the actual attester is constructed, which TEE chip it is, what's the architecture that it uses. But this notion of having attesting layers here is common across the industry in some fashion, right? Some things have a very small number of layers, other things have a large number of layers, but this notion of layers is very common. So the point here is once you have a target environment that's been signed, then it can then become a testing environment for another one, and you can have this chain, okay? So that's what we mean by layered attestation or layered evidence. It's really a statement about what goes in the evidence. So that was an example blowing up inside the attester, okay? Well, there's also cases where what is an attester starts to be more complicated too, because you can have multiple attesters within the same device that are not layered, okay? And a typical example in the IETF comes up in some of the router cases where you have some routers where you have maybe, line cards or things all within the same chassis. So you have one, in this case, the typical term might be used as a lead attester on the left, okay? And it's the one that's responsible for the protocol, right? The thing that actually takes all the pieces of evidence and sends them off. But you might have a bunch of completely separate pieces of evidence, none of which sign each other, that need to be collected because they're all on the same device, okay? So again, in one example, B, C, and D might be different things attached via an internal link or, a bus. If they might be different peripherals, and you have a device that says, I want to attest these different peripherals or line cards or whatever they are, bundle them together, send them off to a verifier and see if the composite device, the whole thing is good or not, right? You can imagine even more complex cases like a car, which has many different subsystems, right? Another composite device. If you wanted to attest that your car is in a good state, that's a pretty complicated thing, right? The point is you can keep adding complexity based on these different building blocks and assemble these more complicated things out of these basic building blocks and still apply the same types of appraisal policy, as long as the appraisal policy is flexible enough to handle these different cases. All right, so how do we map that to protocols? Okay, well, I'm going to give two analogies to real world, like human cases. So one case as humans, right, we're often familiar with passports, right, make driver's licenses and so on. Well, the way this works, right, is you fill out your little driver's license or passport application, you get it signed by usually some government entity, and they give you a document or a passport or a driver's license or something that you can then go around and you can present to people, right? You can say, hey, I'm over 18, so you can let me in. Or, hey, I have something that says, yes, I am certified to drive a bus, that kind of thing. And so I can present that to people and they will believe it because they look at that and it's signed and stamped by a government organization, and it looks like it's not been forged, and so they trust it because it comes with these very hard to tamper with or hard to duplicate credentials like driver's licenses and passports, right? So it's kind of what's going on in the left case. You take a protocol, and so in this case, the government organization, my example, is a verifier. The attester is you, and the relying party is whoever you're going to show your driver's license, your passport to get through, the airport line, okay? And so you're going to present some evidence to fill out your form and present your birth certificate, whatever else is necessary to get your passport. It gives you back the passport. That's your attestation result. Now you can supply this to different entities, okay? And they're going to look at that and say, well, you just gave me a driver's license from someplace I've never heard of. I don't know that this one is correct, right? It's not from an entity that I trust, right? You've got a passport from, Chuck E. Cheese. I don't believe that, right? That's a driver's license. That doesn't mean you can operate on the road, right? It's not in my trusted set, right? So that's kind of how the human model applies to a protocol here. And there are systems built that actually do this exact model here. Second case of a model that can be built with protocols is called the background check model. This is a case where you might be filling out, say, a loan application or a job application. And so what you do is you fill out all the information. You might present some other stuff. You hand it to the relying party. The relying party here is, the bank that you're applying to, or the place that you're trying to apply for an apartment, or the job application, the company, that kind of thing. And what happens at the back end is they take all that stuff, and they're going to send it off and do some various background checks. They're going to look up in some external databases and see if you got a criminal record and that kind of thing. Okay. So on the back end, before they tell you whether you're good or not, they're going off and consulting a verifier, right? The verifier, the relying party, is not the expert in deciding whether your credit score is good. They're going to go off to the credit score agency and just ask them, right? That's the verifier. Okay. And based on what that comes back with, then they'll make the hiring decision or the loan decision or whatever. Okay. So this background check is also very common. Humans understand and use both of these models every day. Okay. Same thing, attestation protocols, both of these are common, and it depends on what your use case is. And so these are reference models, and there can be variations of these, right? But these are the two common reference models that map to things we can kind of all understand because we do these every day, or we're familiar with these concepts because they're out there and we hear about them every day. So let me talk about an example or two of maybe variations or hybrids here. So here's one example where that's using the model on the right, the background check model, but the verifier and the relying party are running on the same device. Okay, so you don't have to go to the anybody external. You've got that verifier and you happen to be running it locally. Okay, that's kind of I don't need a third-party service. I'm kind of doing that myself. I may even be running that on the same system. Okay, that's an example that uses that same model. Okay, but it just so happens that those two roles are combined and running in the same device. Any of those other ones could also be combined. That was just one example that's kind of a popular case that comes up, especially for those that have not done attestation before. Often they'll start with this one and then decouple those roles on different machines. All right, so here's this is taking an example use case of I wanted to provision a workload into a TEE for confidential computing. Right? How would we do that? The IETF has another working group that's around TEE provisioning for cases that you care about. Do I want to put my confidential data into this TEE or not? And it has a protocol called TEEP, or TEE provisioning protocol. So this is an example of how you might assemble pieces there. And so the attester at the bottom left starts off by generating some evidence, supplies that across, in this example, the TEEP protocol, to a relying party, which in the TEEP protocol is called the TAM. Okay, this is the Trusted Application Manager. This is what decides whether it's going to put that workload on the TEE or not, that workload, or need to patch it or whatever. And so in this case, it's using the background check model. And so it's going off to a verifier because it doesn't know about evidence and attestation results itself. It's just the thing that deals with TEE provisioning. I know how to provision workloads and things, but how do I know whether it's good or not? I consult a verifier. Again, could be on the same machine, but in general, it's a different role. The verifier then comes back with an attestation result. Okay, that attestation result is either going to say, based on the appraisal that the relying party does, he's either going to decide that that thing is already in compliance or it's not in compliance. Okay, and so, and again, this whole workflow might happen periodically, for example. And so it might be it's already in compliance, things are good, and I can pass back an attestation result to the attester that says you're good, you can operate, you're already fine, you've already been provisioned with the latest stuff. However, if it comes back and says you are out of compliance, okay, Typical attestation would then stop there and say permission denied, okay? But here what's going on is the relying party is the thing that's provisioning the workload, okay? Or can provision updates to the workload. So it says, hey, you're not in compliance, so what do? I start sending down commands to the T protocol to do remediation. I need to install, first I have to upgrade your firmware. Well, now I got to upgrade your architectural enclave that's part of the confidential computing, the TEE. And so I have to push updates to those, and then I can push down the update, okay? And then I can say, now you're good to go. Now I can give you your attestation result certificate that says you're good, okay? So that's how you can kind of compose attestation into an example of how do I do provisioning of workloads for a secure case. And at the end of the day, what's happening is that workload is then going to do things, right? That workload then communicates with the relying party. And so it's already got that attestation result that it's gotten, okay? That says, I'm already in a good state. So it's got that, and now it's using that part like in a passport model, okay? The workload can then supply that attestation result that says, I'm a good workload because, my provisioner has given me the certificate that says that I'm good, and I can then supply that and get access to the different things that their other relying party are trying to do, healthcare data, whatever it is. All right. Let's finish up with a couple things here. There's many different formats for evidence. There's also many different formats for attestation results. I mentioned that attestation is not new. There's plenty of proprietary systems that are out there today, right? Many processor manufacturers already have one, okay? Many organizations that are special case have one, okay? But how do we do a standard such that you could use a common verifier for many different use cases, okay? So on the left, this is showing many different pieces of evidence that could, in theory, come into the same verifier and generate different attestation results, okay? Why is that? Well, your relying parties, okay, if I go back one slide, remember this was potentially a pre-existing line, right? This is saying, I'm trying to add attestation into something, okay? So what that protocol can carry in terms of credentials for authentication, okay, which I think one of you mentioned a question about the relationship to authentication. If you've already got a way of carrying authentication data, and now you're trying to add attestation data into that, being able to reuse the same type of format is beneficial because I don't have to change the protocol. That's one of the reasons that RATS is not trying to do protocol changes, because for a lot of those, the hope is you can use existing protocols, but there's many different protocols. We want the RATS formats to be carryable inside existing protocols that have not necessarily all the same format today, okay? And so the RATS working group is also trying to do formats, and so far, the things that are in scope is CBOR web tokens and JSON web tokens. Now, of course, you could embed those inside other things like an X509 cert or whatever, but so far the standard has been the term entity attestation token, or EAT, is dual, either CBOR or JSON. Both mappings are present and they're both called an EAT, even though there's two different formats. And that's because the data is sort of isomorphic. You can convert one to the other, right? And so how do you do those while still allowing the verifier to accept other formats besides EATs, right? So for example, attester C, talking to your relying party W, might supply evidence in one format, but the verifier has to understand a proprietary format, maybe one that already exists today, and supply it to a relying party W that might expect to use the EAT standard format in CBOR format, okay? And all that is supported in this architecture by saying it's the verifier's job, not just to apply the appraisal policy for evidence, but potentially to convert the actual format in which the same type of claims are expressed. All right, last topic, and then I'll open it up to the other questions here, is about freshness and replay protection, okay? Which is, once you have evidence, it's not sufficient to just say, here are the values and the values are the correct values, okay? There's an important security consideration here, which is you have to know that the information is recent, not a replay, right? It could have been exactly the correct evidence as of a week ago, and now it's in a bad state, but it wasn't when the evidence was generated, okay? So if you think about the passport example, I don't want to supply an expired passport. Well, how long is that passport valid for, okay? Well, in the passport literal case, and for humans, right, it might be valid for 10 years, right? Because that data tends to be data that doesn't change, right? But how do I know in the computing case that that is still the correct information? Because there might be information that was used that could change at any time. Like as soon as malware gets in there, all that information is out of date, right? So how do I know that the evidence was a recent set of evidence? And how do I know that attestation result, if I'm a relying party, how do I know that that's recent, okay? So just like someone would check the expiration date on a driver's license or a passport, how do I do that in computing where we're talking about much shorter lifetimes? Okay. And so exactly how recent is again up to the appraisal policy. So how good is good? What's the definition of good? That's up to the owner of the verifier, the owner of the underlying party, to specify in the appraisal policy. So the appraisal policy now includes not just what the definition of the correct state is, how to compare it to reference values and things, but also how recent is okay. Okay. Does it have to be generated a microsecond ago? Well, then network protocols are a problem, right? Because your propagation delay is longer than that. So how recent is okay? What's the window of out of dateness you're willing to live with as part of the appraisal policy? Okay. I'll give you 3 common ways, and I'm not going to go into the details of these just in the interest of time, but feel free to ask a question about them and we can come back. I'm going to give you the real brief version, like 20 seconds, 30 seconds each, and then we'll open it up to other questions. Okay. So first method is I put timestamps in them. Okay. Now, if I put timestamps in them by the generator of evidence or attestation results and the receiver of evidence and attestation results, and I can look at that timestamp and I can say, is this recent or not? Okay. Well, the problem with timestamps, although it can be a good solution, is that it requires you to have synchronized clocks, or at least close enough synchronized clocks. Okay. That means you also have to have a trusted source of time, which for confidential computing is still a challenge in many cases. Okay. I have to have a way that something outside the TEE can't spoof the time. Okay. So that's actually a challenge today. You need something like NTPsec inside the TEE and so on. So we can go on, you can kind of extrapolate from there. If you have questions, let me know, but this is possible. There are people that want to do this, but it does have challenges with existing hardware in many cases. Second category, we use nonces. Okay, well, great. The receiver of the information supplies a nonce, and the signer of the evidence or attestation results puts in the nonce and supplies it back. And so you know it was generated since you generated that nonce. Okay, and so that way there's no dependency on clock synchronization or even having clocks in the first place at the senders, but the receivers have to remember whether that nonce is good or not. Okay. So in the simple case, you'd have to keep state in all those nonces. There are various optimizations for that. If you're familiar with like how SYN attack protection works, you can imagine different things you could do for minimizing state for nonces, right? And the receiver, right, the relying party for attestation results and things needs a clock to expire the nonces. How do I know if I sent a nonce when that nonce is no longer good? Okay. So I still got to have a clock on the receiver side, but maybe not on the attester side. And of course, this only says, was the signature generated recently? It doesn't provide any faith that the information that the evidence was signed was recent. So in other words, if I booted a month before I generated the evidence, then the information in the evidence might be a month out of date. Have you guaranteed that it couldn't have changed since then? Well, if it's immutable after a boot, maybe, right? But there's this other aspect you got to worry about too, where timestamps can often do that because you have to have timestamps on the values. And this one, you can't do that. Third category is epoch IDs. Okay. This one's like nonces. It's sort of like a hybrid between those. Where you have a third party, a third entity, sort of like your clock synchronization server, except for in this case, it's not a predictable timestamp. It's an unpredictable epoch ID. And so everybody gets the same epoch ID, okay, but it's been unpredictable. So you don't know what it was going to be before then, okay? But so now you can supply that just like you would have supplied a nonce, and everybody else who got it knows that you have one of the most recent ones because you couldn't have predicted it, okay? And so in this case, you can keep the state down fairly easily, but again, it introduces this dependency on this third entity that you put in that you have to trust, okay? But then if you do something like this, then there are ways to do it such that the only thing that needs a reliable clock, by reliable, I mean secure in a confidential computing sense, is the epoch ID distributor. Okay. And so anyway, more details are inside the architecture, but again, each of these are categories for constructing solutions. It's almost like tools in a toolbox. Any particular solution might not map to any of these 3 methods identically, right? But these are categories from which you can construct solutions. But the architecture is robust enough that says, doesn't matter whether you're using nonces or timestamps or epoch IDs, this architecture is the same architecture. And so the document talks about how you might apply any of these techniques when building a literal solution. Okay. So with that, I'm going to open it up to just other general questions and start going back to the things still sitting in our Q&A queue. Please feel free to add some more. Happy to go back to previous slides if necessary. And so I'm just going to go through and probably in order here, since I think we've got enough time to get through the ones that are posted. We'll see. Ben asks, can there be different levels or definitions of good state that different systems may use depending on how good of a state that a system may need? Answer, Yes. In fact, there's some specific IETF proposals being discussed in that exact category. I think, for example, there's a document called trustworthiness vectors. There might be 2 documents in that category that are proposed. If you're not familiar with the IETF, the different stages that documents go through, this is just for everybody, not just about this question. There are people that submit documents to the IETF. Okay, those are called individual submissions. The IETF can then decide whether to adopt a document. That makes it a working group document, and that's a commitment to publish. Okay, and then there's an RFC, which is actually the published standard. Okay, I think the things in this category right now are in the individual submission category. I don't think they've been adopted yet, but I think there was a call for adoption out. So absolutely, the answer is yes, and you'll find information on the link that I put on the first slide about the RATS working group documents, which also includes individual submissions to the working group. All right, Mary asks, the verifier seems roughly equivalent to authorization. Will there be any alignment with authentication and authorization protocols and policies? I think the intent is absolutely. You're right, it's roughly equivalent to authorization, except for it's not quite equivalent. It's actually stronger than classic authorization. Now, classic authorization says, I believe you are who you say you are, okay? And that I'm going to then make a choice to allow you to do a particular thing, right? So you've authenticated and I'm going to authorize you to do an operation. What attestation does is adding another piece to that, is just saying, not only do I know who you are, I also know that you're in a good state. And then I will grant the authorization, okay? So you can think of attestation as being something in addition to authentication that you use as part of authorization, okay? And in that sense, we absolutely want alignment with authorization protocols. Okay? And that's one of the other reasons, as I mentioned, that the RATS working group is not chartered to do protocols, right? The intent is to try to reuse the existing authorization protocols that already exist. So hopefully that answers your question. All right, Penguin asks, the role of verifier and lying party seem very similar. In what condition the verifier and lying party could merge together? Okay, so if I go back to the slide that showed this one here, the verifier and the lying party, if they are run by the same entity, by the same organization, and they can run on the same device, then you might merge them together. Examples of where you might want them to be different, okay, is if I have heterogeneous relying parties. Okay, I have either a bunch of different types of services that I want to use. I mean, like let's say I'm running different types of banking systems, both the publicly accessible ones and my internal ones. But I want to reuse the same verifier because a verifier needs to be, a highly available service, and I have a different team managing that. Then I want to run a verifier on a different machine, and so that's where you can provide the separation. Another example is I have relying parties that might be running on different processors, right? I have heterogeneous devices. I'm a multi-vendor system that I have, say, 2 different TE vendors, and I want to use the same verifier, right? Then of course they would not be on the same one, but many people will start with them on the same one. All right, Ben asks a great question. I think that answers Dale's question too. Can the verifier be the same entity as relying party? Answer, yes, that's what this slide is showing, is they can be the same thing. They're 2 separate roles on the same device, or potentially even in the same software, but they're really 2 conceptual roles. Okay. So Ben asked an important question, which is worth elaborating on. How do you attest or gain trust in the verifier? All right, excellent question. Okay. Let me go back to, I'll just go back to maybe this slide here. Okay, so I mentioned the verifier has to trust these other entities up here, right? It's trusting, an endorser, reference value provider, or verifier owner, and so on. The relying party trusts the relying party owner and the verifier, right? But how does the relying party know that the verifier hasn't been compromised? Great question, okay? So when we talk about this one, we say, well, typically, the way that you want to solve this for a very strong level of security is you want the verifier to first act as if it were an attester talking to a relying party, okay? So this is a case where this model, right, the one that we were just talking about where you combine them, this one here, where when the attester is the verifier, okay, the verifier that all the other attesters are going to use, you have to say, how do I know based on the verifier's evidence that is a good verifier? How do I know that I can trust it? I can authenticate them, but how do I know that the verifier is in a good state? So for that one, the common case is to say, I have a minimal verifier inside the same relying party box that's only capable of verifying the attester's evidence. Does not have to be general purpose. Does not have to deal with all possible claims. okay, like a normal verifier would be. This could be a special purpose verifier, a very lightweight one that only understands the types of evidence that the verifier would provide as his evidence, okay? And then you can have a very simple policy inside here that can do just the verifier's evidence, but not have to deal with all the complexity of all the other ones, and offload all of that to the verifier, okay? So that's another example of where this model right here comes in, is exactly how do you know that you can trust the verifier, okay? Great question. All right, let's see. Mary asks, which, if any of these steps could be vulnerable to side channel attacks? In theory, well, all of them. How can you prove that they're not? I guess that's the short question, the short answer. There's a longer discussion of side channel attacks inside the technical deep dive white paper from the CCC that's linked on like the first or second slide. For a longer discussion, I'd point you into there, but I guess the short version is pretty much all of them could be susceptible to side channel attacks. And so that's why side channel attacks are part of the threat model of the CCC. All right. Dale asks, are there any plans to build an open source reference implementation of the spec? Okay. Two questions to of that. So from an IETF perspective, the IETF doesn't do reference models, but it loves when other people do, but it doesn't call them reference models. It just calls them implementations. And in fact, the IETF loves there to be two implementations that are completely independent, because that's what helps verify that the spec is well written, because if two people can implement things and be interoperable, then the spec is well written. So the IETF likes two implementations as opposed to a reference implementation. Okay, IETF head off, CCC head on. Within the CCC, the TAC has chartered a SIG, special interest group, on attestation. And the attestation group is trying to talk about how you'd build reference implementations of specs like this. And so as an example, there's one project that's been presented to the TAC, and I think it might be a topic for an upcoming webinar. So stay tuned for news in this series on implementation of an open source verifier. And so are there plans within the CCC? There's certainly discussions to do that for open source code on the verifier. That has not been contributed yet, but it's been presented, and it might be presented as a CCC project, but since that hasn't happened yet, can't commit to that, but there are certainly plans of people doing that now, is the short version. All right, I think we're getting close to the end of time here, but I think we had a couple more minutes, so let's see what else I can get here. Muhammad asks, in a standard formal design procedure, a standard is specified first, and then the implementations are developed following the standard. In this case, all standard TEs have their own attestation procedures, and standardization is still under development. I don't expect any one of them will change their attestation. What's the motivation for the standard then? Who will be the end user of the standard? Okay, that is a great question, because that's a question I asked within the IETF myself. Okay, so I'm going to go back to that, the one that is on the bow tie flavor, bow tie shaped one. This one. Okay. All right, so if you think about the context of Muhammad's question here, right, he's talking about how you have a bunch of different attesters here being the things that generate signed evidence, okay? At least I'm going to take an answer whereby the things with the standard TEs are attesters over here. So you might have attester A might be SGX, and attester B being TDX, and attester C being SEV. Of course, forget the label that's on here, right, in Muhammad's question, okay? So what is the motivation for this architecture? Well, many people, I would not speak for the entire working group, but I would say many people in the working group, their use case has to do with the right side here. It says, even if everything on the left here was a proprietary evidence format, okay, say, the SGX quotes and SGX report format, and just take the first of your examples here, there's still a need to say, how do I write a relying party that is the same relying party, regardless of whether the thing on the left is, SGX or SEV or whatever else? How do I do that? Okay. And one way to do that is to say, I write my relying party to accept EATs and put on the verifier's job to how do I translate, say, that SGX report into an EAT attestation result, or generate, an SEV SNP report into an EAT on the right. So this architecture easily accommodates this way of saying, how do I have heterogeneous proprietary formats on the left while still making it easy to develop things on the right that interact with existing authorization protocols? Okay, so there you go. That's the best answer that I have, because that's actually the question that I asked. Other people have other takes on that within the IETF, people that want to have EATs on the left here for evidence. And so if you look at the EAT spec, you see the EAT spec will allow both use cases, Many people that have a question similar to how you phrased it, Mohammed, have the opinion that EATs will be used mainly over here. And so that's one of the use cases. There are other parts of the working group that want to use it on the left, but I can't comment on whether there's any processor manufacturers that want to do that. But you can imagine maybe, say, a RISC-V case might do that, since you can kind of build your own there. So there you go. All right. Let's see. I can probably take one more question here. Let's see. Dale's is easy. Does the standard also specify which crypto algorithms need to use at each steps? Okay. The answer, the architecture does not. That would be up to the protocol. And if you remember, the RATS working group doesn't specify the protocol, but somebody building an actual solution would have to choose a particular protocol and specify those. Well, that's not something that the IETF does right now. Now, what you can say, I can recraft your question here, which is probably maybe the way that you meant it, is a question about the EAT token format specifically. Does the EAT token format specify which crypto algorithms need to be used to sign the EAT and to check the EAT? And I believe the answer to that is yes, and you can check the EAT spec. Now, so far this webinar has been about the architecture document. There's a separate spec about EAT. That one is not in last call yet. There's still opportunities for change. If you have things that you need or you want EATs to do, there's still time, but get it in soon. Okay, so that's really a question that's beyond the scope of this original webinar, but the short version is go and read the EAT spec. I think the answer is yes. All right. So with that, I think we're about out of time, but Ashley, anything else you want to wrap up and bring us home on?
No, just thank you so much for the great presentation, and thank you all for joining. A recording of today's presentation and the slides will be available on YouTube shortly, so you can check out this webinar and other CCC webinars on the YouTube channel. Thank you everybody for joining, and I hope you have a great rest of your evening.
Great. And if I didn't get to your question, I think Mohammed still had two other questions I didn't get to. Feel free to put them on the TAC list, or even better, on the IETF RATS mailing list. And we want to make sure all questions can get answered. And if there's anything that's not easy answer, that the IETF working group will take them into account as they're revving and finalizing the spec. So thank you all for your great questions, and thank you for coming.
Thanks everyone. Bye.